And for our First Alert weather team, our meteorologist posted pictures on social media, which I so enjoy because you guys are so good at showing us what's happening all over the state. And we saw some funnel clouds yesterday, or an air funnel, and people wanting to know, is that a tornado? What exactly is that?
Okay, so it's probably tomato to a lot of people, and I understand that. Kathy Doyle shared this video with us of a cold air funnel near Tonkawa yesterday. So it's not a tornado until it touches the ground. It's always that way, whether it's a cold air funnel or a normal funnel. Once it touches the ground, that's when it becomes a tornado. But these yesterday, they formed in cold air instead of warm air. What difference does that make to you? Well, that means if it did come down and touch the ground, actually form that tornado, it would be really, really weak. These winds in these cold air funnels usually stay less than 55 miles per hour, and most of them don't ever come down and actually touch the ground.
After some early day storms, another weather phenomenon yesterday caught people's attention near Oshkosh. A funnel cloud was spotted over Lake Winnebago, what's known as a cold air funnel. Fox 11 meteorologist Phil DeCastro explains.
Cold air funnels are different from normal funnel clouds that you'll see from thunderstorms, and Sunday's weather setup was actually a perfect example of it. We had a strong low pressure system and cold front pass on through. Now this brought in cool air on blustery northerly winds, and this large area of low pressure also provided plenty of what's called vorticity, and this is essentially a measure of spin in the atmosphere. Now with cool air aloft, air that was warming up near the ground was allowed to start to rise. But as the air starts to rise, it also stretches out this column of air. And with all the vorticity and spin in the atmosphere, that air also starts to rotate. And as it stretches more and more vertically, it rotates faster and faster, like a figure skater spinning faster by bringing their arms into their body. Now, this process for forming a funnel is different from a normal funnel cloud. Those require large rotating parent thunderstorms. Cold air funnels, in contrast, well, they tend to be much weaker and rarely touch down, as was the case on Sunday. Meteorologist Phil DeCastro, Fox 11 News.
We've received plenty of reported pictures. Take a look at this picture sent from Tim showing the waterspout over Lake Winnebago around 7 last night. And here's another one showing it over the lake, taken from the Southside Ice Yacht Club.
We had a little bit of everything.
We did, and a really interesting occurrence, and we talked about this at 5 o'clock, this gustnado or landspout that popped up near Whitewater. So let me show you, first of all, this is time-lapse of the clouds from the UW Whitewater campus. This is one of our smart WeatherNet sites. So we're looking southwest, and watch the right side of the screen because you'll see this rain shower come in. It's certainly not a severe rain shower by any means, but it's coming in. Of course, there's the rain. This produces think of it as sort of a cool gush of air coming down with that rain. Then that cool gush of air pushes out ahead. Nothing unusual about that. It's in what we call an outflow boundary. That outflow boundary interacted with a lake breeze coming in the opposite direction. Here's sort of a graphical way to look at it here. We'll give you a side view of this gustnado, and in fact, here's the graphic to show that. This occurred near Highway 89 and Highway 12. So here comes this rain shower, and then from the east, coming in off of Lake Michigan, comes the cool lake breeze. That lake breeze pushing in from the east. Meanwhile, the outflow boundary coming in, pushing out towards the east and interacting with that lake breeze. The result is a wind shear that can actually spin up a landspout, or what's oftentimes called a gustnado, something that occurs on the front edge of a gust front. It's not a tornado. It did cause some damage, though, and in fact, these photos courtesy of the Walworth County Sheriff Department. You can see the roof here of this barn was damaged, and some of that debris thrown for several hundred feet. This was witnessed, by the way, by a trained storm spotter and was able to document this, witnessing it very well. So interesting combination that occurred near Whitewater today. Of course, those showers, non-severe, did produce some pretty nice views in the sky, including this double rainbow. Thanks to one of our viewers, Belinda in Delavan, for sharing that with us. 2 pots of gold. That looks great.
Not all tornadoes originate from a mesocyclone or even a supercell. One type of non-supercell tornado is a landspout. Landspout tornadoes occur as the parent storm cloud is in its growth stage, with the spin originating in the boundary layer of the storm. The term landspout was originally coined by Howie Bluestein in 1985 and was named as such because they resemble waterspouts. Another name for landspouts are dust tube tornadoes. Landspouts usually take the form of a translucent and highly laminar tube of dust, perhaps with the funnel above. A landspout will form in an environment with a high degree of low-level instability and typically within higher cloud bases. They're usually weaker in nature and relatively short-lived. Typically, landspouts will move very slowly. Landspouts are most common across the high plains during the late spring months and along boundaries rich in boundary layer vorticity, like stationary fronts.
Now this morning on Daybreak, Storm Team 8 meteorologist Kyle Underwood said from the damage he saw, he thought it was all caused by a tornado. And then this afternoon, the National Weather Service confirmed that, saying it was an EF1 twister with winds up to 110 miles an hour.
So the big question, when that storm hit last night, there wasn't even a severe thunderstorm warning that had been issued for Kent County, let alone a tornado warning. No sirens. They never went off.
That's right, taking many people off guard. This afternoon, 24-Hour News 8's Henry Erb is getting answers about why. He's joining us live in Kentwood near 44th and Kalamazoo. Henry?
In Kentwood, and the only warning that people here in this neighborhood had was the sound of the twister coming itself.
Definitely snuck up on us.
And when it did, 2 trees crushed Andrew Ruster's home. It was over in seconds. He says he'd been watching TV and knew there had been a severe thunderstorm warning earlier when the Weather Service feared hail in Ottawa County. But there was no official warning when the twister hit, except for the sound of destruction coming closer.
I heard like a swirling noise, and then basically ran to the downstairs, the lower level, and then the tree came in right behind me on the steps.
So why no warning? The National Weather Service says this was the kind of tornado that gives the radar no hint it's coming.
It looked pretty much just like an ordinary thunderstorm. The main threat we were worried about was heavy rain.
He calls it a spin-up tornado. Big storms start a couple miles up in the air and take their time working their way to the ground. So radar has time to see them, and the Weather Service has time to warn people. This kind starts on the ground suddenly without warning. He says the radar sweeps around every 4 minutes. This one appeared about a minute after the scan went by.
The next volume scan comes in, and now you're halfway down the damage path before we even see the signature. And then it takes a couple of minutes to issue the warning.
This tornado was on the ground for 6 miles and just 10 minutes.
And they saw evidence on the second scan, but it was already weakening. So they chose to go with a severe thunderstorm warning instead of a tornado warning.
In this part of our training, we'll talk about non-supercell tornadoes and other rotations. A non-supercell tornado is also referred to as a landspout. It has no organized large-scale rotation. There is no wall cloud associated with it, and there is no rotation shown on radar either. This particular example was taken near El Paso in May of 2014. Notice that there is no wall cloud that's associated with this particular circulation. Here's another example from the same area, looking a little more dramatic. It can be nearly transparent at times. Notice that you can see somewhat through it. They often form near a slow moving cold front or a stationary front with opposing wind flow. They can also form on the southwest edge of a cluster of multi-cell thunderstorms. In Illinois, these are most common from late April into June. Here's a video of that landspout that occurred near El Paso last year. Notice how it is very transparent. You can see the clouds behind it. It isn't moving very far, very fast. But it can cause damage if it were to hit something. Another type of rotation that you may see is called a gustnado. This is a short-lived rotation that's along a gust flow or an outflow. This particular radar image All these blue lines that are coming out from the thunderstorms are what we call gust fronts, or outflow boundaries. These are accompanied by cooler air and gusty winds, and these are most likely where a gustnado would form. The rotation does not reach up into the cloud. And once again, we also do not see a rotation on radar. So look for the rotation at the ground, not just dust being kicked up, but an actual rotation at the ground level. These can cause minor damage, mainly from the wind gusts. If you happen to see one of these, be sure to refer to it as a gustnado. Another thing that we tend to see across central Illinois is cold air funnels. They occur in vertically developed clouds, and usually they don't have any thunder with it. They are most common in late spring and early summer, and also again in autumn. Rarely do they touch the ground. Should they actually touch the ground, they could cause some minor damage. Almost always, they occur in the afternoon or early evening hours, and they can persist for quite some time.
Okay, well, this is part 2 of a 5-part series looking at supercell formation and tornado genesis of 2 different types, one with supercell mesocyclones and then the other one non-mesocyclonic tornado genesis, and that's what I'm going to focus on in this part. Okay, so tornado genesis, of course I'm cheating here. We show a picture of actually a supercell tornado. This is the start of the El Reno tornado. Point is, whether it's a tornado like this, or one that looks like this, much more typical so-called landspout look, the basics of tornado genesis are the same. It's just a matter of how you get the ingredients arranged. We need near-surface vorticity, and simply put, a swirly or spin. You need something near at the ground where there's spin, and you need something to stretch that. Now, this is the scary part if you are an operational meteorologist, or even if you storm chase or anything else. How many different types of surface-based thunderstorms cannot possibly have some sort of low-level spin and updraft stretching? Good luck if you think there's any of them. And anyone who watches convection along the Gulf Coast, or say the Florida sea breezes even in the summer, and you wonder, why was there a random tornado or 2 today? Eventually you co-locate some sort of swirly with an updraft. And you see this all the time down by the Florida Keys or in northeast Colorado, where there's something in the background, confluence lines with the islands based on the background flow, or terrain-driven circulations that provide the circulation. And anytime you get updrafts on top of these swirlies, you can get these non-mesocyclone tornadoes. Now, supercells, they just provide the vorticity a different way, and it's a more repeatable process, and it's more internal to the storm, and we'll talk about that more in part 3. Okay, non-mesocyclone tornadoes, here's just an example. You don't have to memorize every little detail of the diagram. The point here is that typically we're looking for some sort of cyclonic shear boundary in the low levels, and we're talking about vertical vorticity is already present along the boundary. So there would be a cyclonic change in the winds across the boundary at some level near the surface. You get updraft development atop the boundary. It concentrates the vorticity and the convergence that rearranges and tightens the circulation, and then stretching of the deeper updraft can result in tornado genesis if we have sufficient stretching and vertical vorticity. Now, sufficient is not easily defined. On what scale? We don't observe the winds and vorticity on the scale we need to say for sure that there's enough spin and enough stretching to amplify to tornado proportions. But we can say, at least conceptually, cyclonic shear boundaries with deep developing updrafts are a likely location for non-supercell or non-mesocyclonic tornado genesis. So again, we're just looking for the swirlies, and we're looking for something to get an updraft going atop the swirly, which the boundary is a natural convergence source. Now, there are plenty of other ways you can see this with, on the lower left, these occasionally spectacular examples. I believe that's from the Mediterranean, but with series of vortices that get amplified into waterspouts along convergence bands. And then on the right, this is one from, I believe, western Kansas, where you see something similar over land with just, it's a little bit drier environment. Point is, if everything works right, you can get a whole series of these tornadoes, and some of these occasionally can produce significant damage if they happen to be sitting somewhere where they form.